Hello, students. Getting into chapter 13, dealing with a little bit of linear measure. Now, this problem at the beginning is really pretty cool. It looks like it's going to be very, very complicated to find the perimeter of the pink region. But when you really look at it, you're like, well, wait a minute. What is the perimeter of the pink region composed of, right? Well, it's composed of a couple of chunks. Let me get a thicker pen here. There we go. So the pink region has a chunk right here, and that is just a half circle. Now the circumference of the big circle is 120, so that's helpful. So C equals 120, and remember circumference is 2 pi times the radius, or you could say the circumference is just pi times the diameter. All right. So that means that if this equals 120, that the diameter is 120 divided by pi. That's the diameter. Well, the radius then would be half of that. So the radius would be 60 over pi. And I want the circumference of this component. But remember, the circumference, right, is what? Pi times the diameter. So the circumference of this one right here, I only want half of it. So it's probably better to say the circumference of the smaller one would be 2 pi times the radius, but half the circumference would be just pi times the radius. So take this radius right here and multiply it by pi, and this chunk right here along the edge is actually 60. And what's beautiful is this component, this next chunk of the perimeter right here, is the exact same piece. It's also the semicircle. So this little chunk right here is also 60. And the last chunk that remains is along the outside ridge. And the outside ridge, let's see. Oh, there we go. And the outside ridge is, sorry, I was clicking the wrong area. And the outside ridge is right along here. Well, that piece is 1/4 of the circumference of the entire chunk. So if the entire chunk is 120, this piece over here is 40. And so you can actually see that it's not going to be some crazy piece, a 60, a 60, and a 40. And so there you go. Kind of a cool way of using formulas visually. So I really do enjoy that problem. All right, let's take a look. We are coming into Common Core standards. These start as young as grade 2, when we're studying volumes, measures, masses, conversions, up to grade 5, where we're doing volumes and volume formulas for prisms. It continues on into grade 6 and 7 with area, surface area, volume, circumference, circles, and of course the Pythagorean theorem really hits us in grade 8, although you will see it previous to that. This one is applying the theorem and studying the volume of cylinders, cones, and spheres. So as we take a look at the linear measure, there are two common systems. The English system, often referred to as SAE, Standard American English, and the metric system. The metric system is a little bit easier to use, as we might be able to see in class. Here are the conversion factors that I need you to know. So I'm going to put a little check mark next to them. Yes. 1 yard is 3 feet. You need to know it. 1 foot is 12 inches. Yes. And 1 mile is 5,280 feet. You do not need to memorize or know the yards because you can convert from feet to yards. So that is completely up to you. But you do need to know those because we live in America. And we're going to use the system of America most frequently to our unfortunate amount of memorization of random numbers. So converting units of measure, what we can see is the way they're doing it is they're just doing a straight multiplication. I believe the best approach is what they do second, which is called dimensional analysis, which is creating unit ratios. And again, a unit ratio is a ratio that's equivalent to 1. So when you write the number 1 in like a big fatty number 1 like this, you're going to create a fraction with the same thing on top and bottom. It could look like this: 12 inches on top, 1 foot on the bottom. And the reason is that those two are equal. Those are the same, and therefore this creates 1 unit. Okay, the unit is the number 1. So you need everything equal to the number 1, and then as you multiply, you're never going to change the value. So 60 miles per hour, watch what they do. They rewrite this as 60 miles over 1 hour. Then they use a unit ratio right next to it. Why? 5,280 feet is 1 mile. So that becomes the 1 right here. They use another unit ratio next to it. 1 hour is 60 minutes. And they use another unit ratio next to that one, which is 1 minute is 60 seconds. So it's basically 60 miles an hour times 1 times 1 times 1. But we choose 1 in a nice way. If you have miles on top, then you put miles on the bottom in your unit ratio so that the miles unit will eliminate. Notice at the end, I wanted feet per second, so feet remains on top and ends up as our final value. Next up, we have hours. Hours are on the bottom. You can see that here. So put hours on the top. That way they eliminate. Now we have feet per minute. We can convert from minutes to seconds by putting minutes on the top, seconds on the bottom. And now we have feet per second. And that is what we wanted. Lastly, grab your calculator and just, I mean it seriously, just type it in from left to right. I'll pop up Desmos just to demonstrate quickly how to do this if you're having any trouble. Here we go. Math tools. I don't know. I could do graphing or scientific. Doesn't matter. Okay. So we simply type it in. Type in 60. I can't even see my screen because all the little menus here. 60 times 1 over 52. Times 5280. Times 1 over 60 times 1 over 60. And what shows up on the right-hand side is 88. Right over here, 88. So that tells you it's 88 miles per, or 88 feet per second is the same as 60 miles per hour. All right. There we go. Historical note: the yard was defined in 1832 as the distance between the 27th and 63rd inch on a certain brass bar made by a company. How about that, huh? In 1956, it was redefined in terms of the British bronze yard, which was actually a tiny bit longer than the Troughton yard. And in 1893, the yard was redefined in the international meter, which is 3,600 over 3937 of 1 meter, using an 1866 U.S. law making the practice of the metric system permissible. Yeah, the U.S. law had to be passed that would allow us to use the metric system. That's how amazing it is. All right, the meter in 1960 was redefined in terms of the wavelength of light from a particular element, in this case, krypton 86, and later in terms of the distance light travels in 792,458 of a second. Nailed it. So there you go. All right, so in 1959, the yard was defined in terms of the international yard, and 1 inch is basically kind of the quickest way to think about that, which means 1 inch is 2.54 centimeters. And that is how we can convert forwards and backwards from yards to inches to feet to meters, all of those. But if we're staying in the same system, the way that they're doing it here is because sometimes they will do it both ways. They show 2 different ways. They show just really understanding fractional components and thinking of it as fractions. I think of it as rewrite it as unit ratios. That is my preferred approach. I think students tend to get those wrong they get them incorrect less often when they do it that way. The other way, oftentimes they'll mix up which one is supposed to go where, and the unit will be significantly off. Okay, so that is my preference. However, I will not mark you wrong if you do the other approach, as long as the result is correct. Okay, metric system. Yeah, We don't really use it too much. However, there was a law passed that says everything labeled in this country is supposed to have both metric and American units on it so that we can see both, and as a way of kind of getting us used to that, right? So anyway, there's some interesting pieces. All right, in class, we talked about a way to remember this. These are the metric systems. So we have kilo, hecto, deca, deci, centi, milli. These are the big ones that we're going to use. However, as they've noted, these three are rarely used. You still need to know that they hold a place value. And you'll notice each one of them is a factor, which means we're taking whatever base unit there is, multiplying it by this concept. So that if we say something like 2 kilometers, sometimes we would call those kilometers. We pronounce it a little different for some reason. By itself, kilo, we in this other unit, kilometer. Okay. So anyway, there goes that. But 2 kilometers, all it really means is it's 2 times this factor of the meter or the base unit. So this would be 2,000 meters. All right. In class, what do we have? King Henry's dear mum drinks chocolate milk. And if you remember that, those are your place values. And again, this D should be a DA. I always forget that because it's weird to have all the others as a single letter, and that one doesn't. All right, KHDMDCM. So what else do we have? Kangaroos have dry mouths during certain months. That's right, those kangaroos in the dry months. That's right, they get dry mouths. Or as I said in class, I let my other students try one, and they came up with kids have drugs, moms don't care much. I think moms do care, but I'll leave that to you. Pick one that works for you. Now realize the base unit of m is going to be used only in the section on linear measure. So when we're doing a linear measure or lines, we'll use a meter. Okay. After that, if we do volume in the metric system, we would use a base of a liter. So it would be KHDLDCM. So that was where we would have a, let's say, a milliliter. Okay. And that would be 1,000th of a liter. You'll notice this probably on water bottles. Water bottles tend to be about 500 milliliters. If you want to convert that to the kind of the American system, it's probably around this fluid ounces, because that's what we would do in our country. So when you say, hey, give me a 16-ounce bottle of water, that's great. It's probably not 16 ounces. It's probably 16.9. And that way it can be marketed around the world as it's just easier, half mil or a half liter. Okay. All right. So how do I use the metric system? The metric system can be used by simply taking steps. So let's go down and we'll kind of take a look at how they do it. They do it with this kind of weird stair-stepping method. Not my favorite, but I totally understand the idea of trying to get someone the whole idea. They'll actually just kind of start, as you notice, they'll just kind of move the decimal each time one place to rewrite it. They're basically saying these are all the same concept. It's all the same value. It's just different units. Okay. All right. It is possible to convert units. From the chart, we count the number of steps from one unit to the other and move the decimal point that many steps in the same direction. Now, that is fantastic. And to me, it's also a little bit long. So if you have King Henry's dear mum drinks chocolate milk, and you have this one which says 1.4 kilometers, and you want to move to meters, what I said in class is think of yourself being right here and just walking 1, 2, 3 steps. Notice it was 3 steps to the right. So write down 1.4 and then move the decimal 1, 2, 3 places to the right. That's where the new decimal is. Anything that doesn't exist, put in zeros. So this would be 1,400 meters. Okay, try the next one, 285 millimeters. Okay, well, now millimeters are down here. Millimeters, and I want to put that into meters. You got it. 1, 2, 3. So write my number down, 285. Here's my decimal point and move it. Notice which direction I went. I went from millimeters to meters is to the left. So 1, 2, 3, move it to the left. This would be 0.285. And if I want to go from kilometers down to centimeters, once again, starting kilometers, that's 1, 2, 3, 4, 5 steps. So 0.03, and I would move it 1, 2, 3, 4, 5. The rest are zeros, and there you have it, 3,000 centimeters. Okay. Metric system, fantastic to convert with, very, very quick. All right. Let's see here. They do talk briefly about things that are in school. This is from what year is this? Grade 4. So grade 4, they talk about kind of moving forwards and backwards with the metric system. So they are introducing it in the grade schools. You may or may not have had a lot of information with the metric system. That depends on where you went to school. All right. Let's take a look at something known as the greatest possible error. Now, GPE, or greatest possible error, is half of the unit used. So if you measured something to 3 inches, the idea is thinking of this as being 3 inches means that you have some kind of measuring device that goes like to the nearest inch. So you can measure out and say, okay, it's 3 inches, but really it could have been a little short of that, could have been a little bit longer than that. And so if you look at 3 inches, your cutoff for determining where 3 inches is would really be right in the middle, right? Because if something was 2.5 inches, you have to make a choice. But if it was 2.4 inches, you would have rounded that down. You would not have said 3 inches. You said it's closer to 2 inches. So it's almost a little bit to do with rounding, if you want to think of it that way. So what numbers could round here? And you would say 2.5 would round to 3. Again, it's right on the cusp. Remember, 2.5 could have rounded up or down with the same piece. So 2.5 to 3, and up on the top end, 3.5, if you rounded that down, would be right there. So this is kind of the things that would get you to 3 is everything that's in the middle here. So the greatest possible error would be half an inch, because that's what we're measuring in. If we were measuring in half inches, then it would be half of that. So if I measured something as 3, not decimal point, let me just rewrite that, 3.5 inches. And remember, my measuring device now goes to the nearest half inch. Hey, that is fantastic. Well, if I'm going to 3.5 inches, which would be right here, then the most I could be off would be at half of that. So the most I could be off would be a quarter of an inch either way. And so this would be the GP possible error would be 1/4, because that's what we're measuring. We talk about linear measure. We're measuring distance. So distance is typically written without the line segment. So AB with a line segment over it, that represents a shape. AB with no line segment over it is a distance. And that distance has to be greater than or equal to 0. You cannot have negative distances. Okay. The distance between any 2 points is the same, going either direction, doesn't matter, from B to A or A to B. And for 3 points, the distance between them has to be greater. So this is what's known as the triangle inequality, right? And the triangle inequality actually says it has to be strictly an inequality if you want it to be a triangle. If you went 2 units from here to here, you went another 2 units from here to here, then the distance going all the way back to the beginning would be 4 units. Unless, right, unless I went 2 units and then I went 2 units this way. Now the distance back to the beginning is not exactly 4 units. It's a little bit less than 4 units. So that's why the sum of 2 pieces has to be bigger than or equal to the third. It would be equal to the third if it's a straight line, if they are collinear. It's not equal if they form a triangle. And that's why sometimes we refer to part of this as the triangle inequality. All right. They'll ask you if you can you build this type of thing. Again, nothing wrong with that. You're just adding 2 pieces up to see if it makes it. As we come into perimeter, the idea of perimeter is simply this. You're just going to add up the distances around a shape. Now, could we create funky formulas? Of course we could, but it's kind of ridiculous. You're just going to add all of them up. That's the idea. Let's see here. A couple root words here. Peri. Peri is a prefix word in our language. Peri, think about other words like a periscope. So scope is like to look or to see, and peri is around. So peri, the prefix is for around, and meter, the definition of meter is to measure. So when you say perimeter or perimeter, we would be measuring around. So you are measuring around the shape. Don't measure the middle chunk. That will be area. We will do that later. So that's it. That's perimeter. Now we got a great opportunity. So if you're in class, we have a chance to do an activity where we're cutting out pieces of paper, finding circular objects and kind of referencing those. And we get a chance to see something really, really cool, which is even when we do it in class and we cut out pieces of paper, we came out with that the circumference was approximately 3.14 diameters. Now in class, I think we had 3 1/7 diameters was our closest, but that's very, very, very close to the actual value. As a matter of fact, that'd be good enough for most construction work and probably for most work that you do in life. So this is the idea of a circumference, but the true definition, it's not a fraction. The circumference divided by diameter forms an object which is known as a transcendental number, which is super cool. For us, we don't get into transcendental numbers, but we will note that this is irrational. So pi as a number goes on forever, never repeats, never terminates. And that is pretty cool. And I think, let me jump up here and see if it still exists. There is there it is, yes. So find your pi day. So it's in a couple different places. This is piday.org. I think it's this one. Yeah, so you can enter your birth date and it will find it in pi. Where does your birth date start? So let's do leap year. Okay. Is it not letting me? Oh, I might be still loading something. Oh yeah, it's still loading something. Doop 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 doop. Don't mind me. Just trying to show some cool stuff to my students. Let's see here. There we go. Oh, I got to clicking too many times in a row. Sure that never happens to all of you. All right, let's see here. Find a birthday in pi. I guess, yes, you type in your birthday and it finds it somewhere in pi, and it'll tell you like it's the 4,312th digit. That's when your birthday starts. Why do I feel like it's loading ads? I feel like that's what it's doing. There it is. That's why, because it was loading ads. Okay. Let me try the one with my pi day instead, and we'll see if it works. There we go. Okay, find my birthday. Let's do February 29, 2000. Okay, there we go. Scan complete, finding digits. There it is. Found my pi day, my exact pi day. If you look, this is pi, and you can see it's spreading out 22900. That is my birthday, 49,985th digit of pi. So I don't know about you, but that's pretty cool. That is something you could do with your students to have them find their pi day, their birthday in pi. And it does start in the middle. If you scroll all the way in, that actually starts with 3.14. All right, let's see here. Yeah, historical note, it was kind of cool. So over time, people have been trying to get better and better approximations. Archimedes, so this is what, 2,200, 2,200 years ago, approximated it between these two numbers, 3 and 10/71 and 10/70. Notice 10/70 is 1/7. That's what we got in class, is 3 and 1/7. So over here, 10/71, it's like, he's kind of bringing the bottom up a little bit. He knows it. 3 and 1/7 was a little too big, and he comes down a little bit on that one. A Chinese astronomer used 355 over 313. And let's see here. In 2016, Peter Trueb calculated 22. Oh, I got to look at that number. Millions, billions, trillions. Calculated 22,459,157,718,361 fully verified digits of pi. There's something for you if you really need something to do with your life. There you go. So there you are. Arc length. I want you to think of arc length as a fraction of a circle, or a fraction of the circumference. And the reason that I want you to think of it that way is then there's no formula to memorize. The length of an arc is part of the circumference. And you can tell what part it is by thinking about the angle that's being used. So you could set it up as, what angle do I have out of 360 degrees is equal to my arc length out of the total circumference, 2 pi r. So again, now if you want to solve this, if you want to look at this as kind of like an equation, notice there's an angle that we're missing, there's a radius that we're missing. So for any problem, if you tell me the angle and the radius, then I could solve this and get arc length by itself. But I prefer to think of arc length as just take the whole circumference and multiply it by some fraction. So if they gave me a 60-degree angle, then I would put 60 degrees out of 360 degrees, and there we go, and I'm off and running. So I don't need to rethink of it as a completely different ratio or proportion. Okay. So they do have a few problems here. Circumference of a circle with this, the radius of a circle whose circumference is given. So you should be able to solve these forward and backwards. That's why we did chapter 8. We're bringing back a little bit with algebra. Okay. Comparing linear measurements of similar figures. Well, this brings us to a really nice theorem, which is if you have any linear measures, the height, the side lengths, the perimeter, any of those, if the scale factor of two images is the same, then the corresponding linear measurements of those will also have that same ratio. So that's kind of a nice one. So if you know that the side lengths are 3:1, then the perimeter will be 3:1. If you know that the lengths are 3:1, then the heights will be 3:1. So it's really nice, and we're going to need that as we go into the next one with area, because once we see that the scale factor might be 3:1, the area is not going to end up being 3:1, but it will rely on that scale factor. So this is a really good, this is laying the groundwork for what we're going to do in 11.2 and 11.4 and 11.5. Sorry, 13. 13.2, 13.4, and 13.5. All right, so that wraps it up for this section. Hopefully you got what you need out of this. I'll do a short video over the homework and the MCs. For now, off you go.